So guys, let's go over to the discussion moment curvature in continuation of the ductility concepts in beams. So the formula for curvature is given here in our lecture as phi equivalent to the ratio m all over your flexural rigidity EI. And this curvature, as I have discussed to you in the ductility concept, is defined also in terms of the reciprocal of the radius of curvature rho or r, or simply phi is equal to 1 over r, where r is the rate of change of x with respect to the angle, no? Or phi is also the rate of change of the angle with respect to x. So they are actually the inverse or the reciprocal of each other. So in reinforced concrete design, the ductility of the section is made by simply allowing the steel reinforcement to yield prior to crushing of the concrete, with an allowance of say 25% to assure its attainment. So this 25% reduction in the reinforcement ratio or the steel itself is to give allowance to an under reinforcement assurance so as the achievement of what you call ductility is attained. Okay, so I also discussed that in my lecture on ductility. As presented on this lecture is also the familiar strain and stress distribution while when the stress distribution is actually uh, shown in terms of either a rectangular stress block pattern or an actual parabolic pattern as described by the dotted curve. So the graph of the moment curvature is created by considering three stages. So these are now some helpful steps for you to follow in order to be able to plot the moment curvature graph. Okay, but before I proceed with these three steps, I'd like to stress out that this moment curvature is very important when we deal with the hinge or the hinging property of sections when you consider a plastic analysis. Okay, so the hinging of the section in the plastic analysis or the limit analysis is very important. Also in pushover analysis, because pushover analysis consider the hinge property of your section, this moment curvature graph is also very important. So to discuss now the actual procedure, the first step is, of course, to consider first your initial stage, which is then crack elastic stage, where the cracking stress is less than the flexural stress at the tension side. So here we consider that the whole uncracked section, concrete section, including the steel reinforcement. So you can see here a section that represents your first stage depth which is the uncracked elastic stage. Okay, so this is the first stage. This is the actual beam section, and this is the first stage. So for the second stage, the cracked elastic stage, where the cracking stress is equal to or greater than the flexural stress at the tension side, then we may now consider or not consider an area of concrete below the neutral axis. And since this is on the tension side, all of the fibers of concrete here are assumed to be ineffective. Therefore, uh, we assumed it. We assume that the burden of carrying all the tensile load is given on the steel. But of course, here the steel is introduced as a transformed area equivalent to N, which is the modular ratio multiplied by AS. Here, the steel is represented by, again, a transformed section equivalent to N minus 1 times the area. So you might ask up at this point in time, kung hindi nyo nare-recall bakit may minus 1 doon, the minus 1 here is to accommodate or compensate rather for the what? The displaced concrete, no? So meron tayong negative concrete area doon eh. Yung laman nung pinanggalingan ng steel mo. Pag tinanggal ko yung steel ko dito, magkakaroon ko ng negative 1 times AS na dapat kong ibawas dun sa total gross sectional area ko. Pero still, NAS pa rin yung ating transformed steel area. Okay? Dito, wala yung minus 1 kasi wala ka namang concrete dito. Ano yung, wala kang displace. Okay? Concrete, not displacement. So this is displaced concrete. Okay, so for the last stage, which is the crack stage, then things are just the same with that of the second stage. The only difference is that since you are on the inelastic stage, your area of compression concrete is reduced by an amount as manifested on the location of your neutral axis. In short, class, another observation that you might put into your mind here is that the neutral axis location what changes its location going in favor of the compression fiber, no? On the extreme compression fiber. Tumataas yung location, yung neutral axis mo. Humihina yung capacity ng beam mo. Okay, from uncracked to a cracked inelastic. Okay, the only difference between these two here, this is still elastic, this is now inelastic. So if we convert this behavior into a stress and a strain distribution, so this is the scenario. No? Okay, we have here the stage 1, wherein the concrete and the steel strains are very small. Okay, so you can see here this line. Okay, so this line, stage 1. So small strain. Neutral axis is a little bit on the lower side, on the lowest side of the beam. Okay, and then on stage 2, it changes its position going to the compression side here. So this is your stage 2. And the strain epsilon increase further, including the steel. The strain increase a little bit more. And at the third stage, you you reach now an epsilon Cu, which is the limit again, because this is an elastic, sorry, this is an inelastic behavior. We only limit your epsilon to epsilon Cu and make use of a strain diagram or a strain distribution that increases your steel strain into a value of uh, epsilon y, or maybe exceeding epsilon y also, no? So this can exceed or be equal to epsilon y. So epsilon y is simply Fy over Es, but of course your epsilon S can be greater or equal to your value here. Why? Because we want the capacity to be on the ductile side. Okay, so ductility is achieved in that case. Okay, so for the stress distribution, what changes here is simply the shape of your stress curve. Okay, so initially this is a triangular or a straight line here. If you will notice on the elastic stage, if this is the graph, you'll notice that this is somehow straight. Okay, and then the curvature will start there up to, okay, so something like this, the PCA block. Okay, so this is now the stage 1. Okay, so here is the stage 1, which is the elastic and crack. And this is the stage 2, which is the elastic crack. And this is now the inelastic crack. Okay, so this is the third stage. Okay, so notice that at the third stage, you don't have any more what? This is a dotted line, meaning to say the concrete at this side will no longer resist any tension, but rather your steel will come into the picture to resist all the tension forces below the neutral axis. And a sudden transformation from a straight line to a parabolic curve here will actually appear. Of course, this rectangular stress block is a witness representation only. It does not it, it is not true. It is just a fictitious representation of what the actual parabolic distribution of stress is giving us. Okay, so that is how the the stages of beam behavior is all about, and that is how you approach the procedure on how to graph the moment curvature relationship. Okay, and the location of the neural axis, this is just a mathematical exercise. So it is determined differently for the elastic and inelastic stage, of course. And if we look into this figure on the stage 1, the neutral axis is moving away from the tension side as the curvature increases from stage 1 to stage 3. So this is what I explained to you about the neutral axis going up, favoring the extreme compression side of the section. Okay, so I'm trying to describe this as the extreme compression side because if the curvature is negative, meaning to say the bending moment is negative, then this figure will simply be uh, illustrated upside down. No? So, babaliktarin mo lang siya. Okay, so this is a mathematical exercise on locating using Varignon's theorem. Okay, so this is just a centroidal location, assuming that your actual steel area is transformed into concrete area here. So I need not to discuss to you how the value of KD here was taken. No? So you just follow how it was done. So I just sum up moments, I think on the top sum of moment of areas equals 0 at the top fiber. No? So this is at top most fiber. So this is your YT actually. It's your top fiber. So for elastic stage crack stage 2, this is the one. No? Okay, you can also make use of a summation at the top, but it's better if you use a summation at the what? At the neutral axis itself. Okay, so this is easier. If I make use of a summation of moment, this is at the top also, but it's easier to do it using at the neutral axis. So it will be 0. Okay. So what do I mean? My formula now will simply be equal to BKD times KD over 2 is equal to NAS uh, times what? D minus KD. So it's easier to solve KD here, okay, than KD here. But they are the same, okay? They are the same. They should be the same because we are using an equilibrium equation. This is summation moment of areas equals 0 at the neutral axis. This is the neutral axis. So you can take note of the exercise there. But I just want to be consistent of taking the area at the top. That's why this is the resulting equation. If you simplify this, it will come up with this one here. Okay? So for your conversion of KD in terms of raw instead of AS, okay, this is the formula. Okay, this I made para yung mga undergraduate, alam nila yung derivation ng KD. Ito yung WSD method class if you want. Use in investigation. Okay, of beams. Okay, so converted in terms of raw. Okay, raw natin. Because the KD in our design, if you still remember, in design, the formula for KD is different. No, KD in design is actually nakalimutan ko na. N something, N over N plus Fs over Fc, something like this. May FC ba dito? So I already forgot. No? So you just take note of this. So this in design, we are using what? The modular ratio. In investigation, we are actually using the actual raw. So this is WSD method. Fs over parang wala itong FC dito. Oh, parang wala ito. But please check it. I'm not using any more WSD. Okay. So in elastic stage, how do you locate the neutral axis. So there's a big difference between the elastic and inelastic stage, because the elastic stage, we are using the property of the section as the basis for our neutral axis, while in the inelastic stage, we are using what? The equilibrium equation as the basis for our neutral axis location. Okay, so take note of that. So in elastic stage, equilibrium equation. In the elastic stage, property tayo. We use material and dimensional properties. Material and dimensional or geometric property. Okay, so this is the one. CC equals T. This is one I'm trying to tell you a while ago, that we simply use the equilibrium equation to get the location. No? So this is your equation in general equation for a singly reinforced beam, and solve for C in this equation. So take note that if the steel yields, we replace Fs is equal to Fy. Okay, so itong As, ito yung Fs mo. So this is particular when Fs is less than Fy. When Fs is equal to Fy, we simply change this to Fy. Okay, so that's the note about this. So also note that these equations are only good for rectangular sections. For your problem set or for other problems, if we consider a T-beam, then we have to apply the intention of the code rather than the formula given by the code. So like in the problem set, I will be giving you perhaps, if we use a T-beam analysis, then you will make this as your T-beam. Okay, ano madadagdag dito pag T-beam? Malalagyan lang ng ano dito, flange, tama? Flange. Walang pagbabago yung formulation. Ang magbabago yung formula, yung equation mo. So let's go now to ductility ratio. So what is now a ductility ratio? It's an extension of the ductility concept, and it's a parameter that defines to us the ratio of the ultimate curvature with that of the yield curvature. So the ductility ratio is just a measure of how ductile your flexural member is. So it's a measure of your expected ductility, which is basically the amount of curvature that is expected after the yield. Okay. Okay, so let's say my graph of moment curvature is like this. So ang measurement natin ng ductility is from this point. Ito yung yield. Ito yung ultimate. Saan may measure yung ultimate? May measure ito doon sa point na 0.003. May measure ito doon sa point ng epsilon C. Yield. Okay? Ano ibig sabihin ng epsilon C yield? Ito yung point ng epsilon C na nag-yield yung steel mo. Okay? So, epsilon C is the strain of concrete when ES is equal to EY, where EY is Fy over ES. Nag-gets mo yan? So, yung ductility ratio mo ngayon, ito yon. Ilang percent? Habang humahaba ito, gumaganda. Gumaganda yung design ductility mo doon sa member na yon. Habang lumiliit, okay pa rin, pero hindi kagandahan. So, yung ductility ratio na to, magbibigay din sa iyo ng measure kung gaano kahaba yung time bago magkaroon ng total collapse dun sa member. So habang humahaba din yung oras mo. Okay? So kung ang ductility mo in terms of factor is only small, expect mo baka after a couple of minutes or hours, babagsak na yung structure mo. Pero maganda pa rin yun kesa yung segundo lang, bumagsak na, di ba? Pero mas maganda kung it will reach a couple of days, couple of weeks, para at least mahabol mo pa siya. Parang ano lang yan, naghihingalong tao, masisave mo pa siya dun sa worst scenario. Okay? So that is the ductility ratio. Ang gagawin mo lang dyan, guys, solve mo lang si Phi tsaka si Phi. Okay, so paano? So the ultimate curvature is determined by considering the elastic crack stage referred to the stress strain below. So ito lang siya. Yung Phi, kukunin mo lang yung ratio nito. Because of small deformation theory class, small deformation means the angle is very small such that the tangent of your angle is simply the angle itself. Okay, so the tangent of phi is simply phi. That's why you simply make use of opposite over adjacent side, you get this one. Where epsilon c is simply the ACI ultimate crushing strain. If you're using a different code, you use whatever value is given that code. And then you solve for C on the basis of this what? Strain distribution rather. Okay? Simply equate C equals T, you can solve for C. You divide 003 to C, you get your ultimate curvature. So, while the yield curvature is simply epsilon y over C pa rin, ano? C. Kaya lang yung C na to, dahil nandun tayo sa verge ng yield, parang WSD pa lang tayo, magkakaroon ka ng KD term dito. Ito yung C mo, no? Okay? At yung epsilon y mo, alam mo na Fy over Es by Hooke's law. No? So, this is simply Hooke's law. Okay? And this KD is simply, what is this side here? This is the elastic crack section. Kung ayaw mong gamitin yung formula na to, you can use what? You can use transformed area method. Parehas lang yan, no? Yung dinerive natin. Okay, so kuha mo na si Phi y, kuha mo na si Phi u, kuha mo na si ductility ratio. You just simply divide Phi u all over Phi y to get this. And in general, this is the equation. Okay? So, kung gusto mong gawin ngayon yung, kunin ngayon or gawin yung moment curvature relationship mo on the basis of actual material and dimensional property to be used in your software, in your analysis, limit analysis, nonlinear analysis, or whatever analysis beyond the elastic range software na ginagamit mo, you can input a very ideal value para yung result mo, confident ka na ito yung mangyayari. Okay, a failure and success in terms of safety is a matter of prediction class, no? In fact, if I hear some structural engineers are hindi naman nila alam kung ano yung talagang strength nung building na ginawa nila, no? Kaya nga yung mga iba na matatapang, they are praying, sige, tumama na si earthquake. Mas maganda nga, lumindol na ng malakas sa Marikina. Sabi, when the threat for the big one is coming, para malaman natin kung tama yung ginagawa natin. Diba? So, it's a matter of prediction. And ang mahirap lang dyan, guys, is pag nagkamali ka, hindi yan isang bagay na pwede mong itama na walang damage. Okay? Buhay tsaka property ang nakasalalay. Kaya yung marami sa inyo na nagtatanong, bakit may naririnig ako, bakit ang hirap pala ng structural engineering sa TSU? Kasi hindi naman tayo magiging ano kung imagine graduate kayo ng TSU with all pride. Gusto namin makilala tayo, no? Makilala yung mga graduates namin um, na doon sa mas magandang experiences. Or dalawang bagay yan. Kung wala ka naman balak mag-pursue sa structural engineering, ang tanong ko sa'yo, ba't ka pa nag-aaral dito sa ng structural engineering? So, ang basis natin dito, class, is for us to be able to really have a feel of developing professional civil engineers to be responsible and accountable for all the things that he or she will be pursuing, no, after he become a master in structural engineering. Yung iba nagtuturo lang, alam ko, pero hindi mo maalis na kahit nagtuturo lang kayo, you will be tapped by other agencies to help, no, maybe on the design and analysis, investigation of very difficult structures. Kasi kung simple lang yung structure, hindi na natin kailangan maging structural engineer. Civil engineers and with their experience and knowledge, yung ating undergraduate knowledge, okay na yung simple-simpleng design. May code na tayo, basta sumunod tayo dun, wala namang problema eh. Ang anticipation natin, class, guys, is what will happen if may problema sa isang building. Pag-aaralan natin yon. So, paano natin pag-aaralan kung wala tayong in-depth knowledge or mastery? Kaya nga mastery dun sa subject. And we will give reports. We will give technical advices that will serve as future basis for the code. Tayo-tayo lang din naman ang gagawa ng code natin at the end of the day. Di ba? Kokopya lang tayo ng kokopya, hindi rin maganda. Pag kinopya mo, kailangan akma. Di ba? Kailangan akma. At pinag-aralan din yan ng ASEP. ASEP ang gumagawa ng code, no? So, bago naman nila in-adapt yung ACI, they have a basis of adapting it. Unfortunately, kulang lang tayo sa resources, kaya hindi tayo makagawa ng konting. But on the side of safety, ACI, the American codes are good, no? Good enough. Okay? So, pag gumawa kayo ng mga pushover analysis ngayon, sabi sa inyo, okay, hey, Engineer Anferni, please, may I know how much earthquake can my building resist? You cannot use NSCP on that because the NSCP only guides you to do some basic code requirement. And since you are a master in this, you have to at least tell your client something that is what? Realistic, predictive. I hope you know what I mean. Pag inatrasan nyo yun at sinabing you are a graduate of Tarlac State University, kawawa naman kami. Kawawa naman ng TSU. Sasabihin nyo, hindi ko kasi kabisado. What? You are a master of structural engineering? You don't know what? Okay. So, medyo challenge na rin sa inyo yan. No? That's why we're not strict with how we implement it. But of course, we are strict when it comes to compliance on our requirements. Okay? Pero sabi ko nga, mahirap naman yung masyado tayo na stress. So let us enjoy the learning, okay, the learning experience here in MSCE by way of exchanging experiences, class. So yun ang maganda doon, no? Experiences, notes, question and answers, kwentuhan tayo. Kaya nga ginawa natin yung MSCE chat. Pero napapansin ko walang nag-chat-chat o hindi lang ako na notify Pero maganda dun tayo nagdi-discuss ng concerns natin. Not only in the lecture class, also in your projects. Kung may project kayo na may problema, we can share ideas. Of course, hindi lang specific kasi meron din tayong uh, trade secrets na dapat protektahan. Pero in general, when we are talking just of some discussions like moment, curvature, etc., we can actually talk about it para maging realistic naman yung mga ginagawa natin. Okay? So, I hope may mga bagong batches ng students ngayon, they will understand me. Kasi ang napansin ko, they come and go. They come and go. My students come and go. Pag nakita nilang very demanding si sir sa hindi na sila mag-i-enroll. And I'm not, I don't know kung naintindihan nila yung reason. Pero they just disappear without even chatting me. Doon lang ako nagtataka, no? So please don't hesitate to communicate with me, and I'm happy meron naman natitira like sila Jeffrey, sila Alan, sila Amperly, sila Paul na bumabalik pa rin kahit na hirap na sila. And this will pave the way naman after konting trimesters pa. Hopefully you will complete your requirements in MSCE. Okay? So please feel free to ask. Ayan, pumasok na si problem set number 2. But since you are not yet finished on problem number 1, marami, I will not set a deadline on this yet, no? So hanggat hindi yun natatapos, siguro next week na natin pag-usapan yung deadline dito. But I just want you to plot the moment curvature graph given a rectangular beam subjected to a positive bending moment. Yun lang. Consider the three-case scenario that I mentioned. No? Ito yung three-case scenario na ginawa ko. No? Sundan nyo lang yung topic dyan. And tatlong case lang yung binigay ko din dito. Akma dun sa tatlong stages na diniscuss ko. Yung una, tatlo yung graph ninyo. No? Yung una, gawin nating AS equals AS balance. Pag AS equals AS balance, ductile pa rin yan, class. Kaya lang wala kang factor of safety for possible brittleness. Kasi wala kang minultiply na 0.75. No? Yung case to ductile din yan, ito yung more on seismic provisions of the code. Ewan ko yung bago, pero kami, because we are already old designers, we're using 0.5 raw balance as our raw max. Okay? Although this is for singly reinforced class, no? These two here are for singly reinforced class. The real situation, singly reinforced beam. The real situation is a doubly reinforced beam. Okay? So for a doubly reinforced beam, ang gagawin mo lang dyan, for a ductile response of your beam, considering seismic forces, ang code natin is restricting us to have a delta AS or a difference between your tension and compression steel area to be 1/2 of your AS balance. Okay, so this is for a double reinforced beam. So ito yung scenario na gagawin nyo, tatlo. Tapos ang gagawin nyo lang, solve nyo yung itong 3 stages ko. Solve nyo yung uncrack elastic. Itong uncrack elastic, crack elastic, kukunin nyo lang yan. Tapos, tsaka yung inelastic crack. Tapos nun, pag nakuha nyo na, kukunin nyo lang yung moment versus yung curvature. Okay, ano yung curvature? Curvature, yung definition natin dun sa kanina is simply ES, epsilon ES, ano yun? Yan. Wala. Andito yata. Doon sa last, ano ito? Ito yung ductility ratio na to eh. Yung sa topic natin on ductility. Yan, dito tayo. So, curvature is simply, sana yun? Yung graph natin. P. Okay, so dito na lang natin isulat. But this is the scenario for ultimate. So I'd like to remind you that your curvature is simply defined on the basis of your epsilon c all over c. Okay, so c here is actually kd on your WST. So for a particular moment, let's say I will iterate on epsilon c, where this is a function of your phi, okay? And phi is a function of epsilon c. Whatever is epsilon c here will give you the value of phi. So this is again a function of epsilon c. Okay? So ganun lang ang gagawin nyo. So when I iterate epsilon c, I simply solve what is the value of the moment. So if you will do it manually, ganun lang. This is an epsilon, this is phi, this is moment. Okay, but phi is a function of epsilon c. Okay, so epsilon c. So whatever you iterate on your phi here will give you a value of your phi there. Say this is phi1, epsilon 1. So you substitute phi1 here to get your m1 here. Okay. So phi1, m1. And then you again make use of epsilon 2 to get phi2 there. And you measure epsilon 2, or sorry, phi2 here to get another m2 here. So it's just a trial and if you are doing it manually, okay? If you are doing it in MathCAD, and then this is just a functional expression. May equation ka lang. And how does your equation, where will your equation come from? Your equation will come from the concepts on moment and curvatures, and also strengths. Okay, so I hope you understand what I mean. So anyway, those who are thinking of problem set number 1, I recommend you finish first problem set number 1. But those who are already almost finished and already finished, you can start doing this problem set number 2. And if you have some questions, you use the group chat, or you can also comment